So in this video we kind of extend the idea of function to a function defined by an integral, and then talk about how to take first and second derivatives of those functions to answer questions about these very new kinds of expressions or functions. Okay, so let's say that I've given you a function just out of the blue. I've given this to you, given you a function f of t. And then I make a new function, okay, capital F of x, which is the integral from 0 to x of f of t dt. Okay, and I ask you the question, can you find some local maxes and mins of this function capital F of x. Okay. So that is the question. Okay. And you have to dig back into your memories to remember how to find local maxes and mins of any function. Okay. To find local maxes and mins, you need to compute a derivative of the thing that you are trying to find the local max or min of. And you're going to set that equal to 0 to find critical values. Okay. But we're fortunate that we have the second fundamental theorem of calculus that tells us how to take the derivative of functions. This is a function defined by an integral. Okay, this is section 6.4. We know that the answer to this, the derivative of this integral, is x times x minus 1 times x minus 3. Okay, which tells you that your critical values are 0, 1, and 3. Okay. We now need to figure out if you have a local max or min at these critical values. How do you determine that? That will require that we look at two derivatives of the function you're trying to figure out if it has a local max or min. This is otherwise known as f double prime of x. Look at the second derivative of the function. But the second derivative is the derivative of the derivative, right here. But the second fundamental theorem of calculus says that the derivative of the integral from 0 to x of any function f of t dt is equal to f of x. Okay. So our function f of x was x times x minus 1 times x minus 3. And we now need to take the derivative of that function, which would be x times x squared minus 3x minus x is minus 4x plus 3. The derivative of x cubed minus 4x squared plus 3x. Here is f double prime of x. F double prime of x is the derivative of this function, which is 3x squared minus 8x plus 3. So how are we going to determine if we have a critical value at a local max or min at our critical values? We're going to do the second derivative test. The second derivative test says test your second derivative at one of your critical values, right? So you get 3 times 3 squared, and all you care about here is whether or not the answer is positive or negative. 3 squared is 9, that's 27 minus 24 plus 3, which is a positive number. So this function, capital F of x, whatever it is, I don't know a formula for it, whatever it is, has a local minimum at x is equal to 3. And the second derivative evaluated at 1 is 3 times 1 squared minus 8 times 1 plus 3, which is going to be a negative number, which implies that this function that we've just defined, again, we don't know exactly what its formula is, but it is a function that has a local maximum at x is equal to 1. Okay? This may be somewhat of an unsatisfying answer because we have determined that a function has a local maximum or a minimum, but we don't know what that function is or what it looks like. Okay? So let's pull up a graph of this function, and then we can start to answer a couple questions and see if our answers are making sense. Okay? So please recall that the function we were given, capital F of x here, right, was an integral. That means that this function is an area function. So there are two graphs that are going to be shown here. The dotted line function, which is the function f of t, and then a solid line function, which is the area function itself. So we could find some values of this area function, but let's test our local max min idea according to this picture. So we're finding the area under the dotted line, so we're getting more and more area, so we're getting positive area. Even though the function is dipping down here, we're still adding up red regions, so our function is coming up. And at x is equal to 1, did we not decide that our function f of x, the solid line, had a local maximum? And we can see there that the function reaches a maximum. If you continue on, we're getting negative signed area, and so we're getting more and more negative area. And finally, right around here, around 1.5, right, we get more negative area than there is positive area, so our solid line function goes below the x-axis, so our area function goes negative. And at some point, we are reaching the point where there is the most negative area possible, and that is why we have a local minimum right here at x is equal to 3. After x is equal to 3, we start to get more positive area, okay, and so our function starts to come up, and from there on, we're going to get more and more positive area. Okay. So our area function, whatever it is, right, whatever formula it is, we know that it has a local maximum where its local maximum and minimum are. Okay. And again, we're fortunate in this problem that you could actually find a formula for this. You could find a formula for the capital F of x function because the function f of t has an antiderivative. That function has an antiderivative. So here is, on the screen here to the left, is your formula for your capital F of x function, your area function. And I'll leave you to show that that's what you get. But just please keep in mind, not all functions that I write down here with an integral, capital F of x, not all functions I write down will you be able to find a formula. This is not always possible. And that will be the subject of the next video. Okay? So I hope you're starting to see the relationship between these functions, okay, and the first and second derivative, and how you can use them to find the antiderivative. How you can use it to find the local max and mins of a function. Okay. So I think the question is probably still a good one. How are you getting the graph of this function, the solid line? How are we getting this? Right? You can always resort, add page below. Okay. Capital F of x, what was it? It was the integral from 0 to x of t times t minus 1 times t minus 3. Right? Okay. Let me move this over a little bit. There we go. So there's our function. What if I ask you to find a specific value? For example, f of, say, 0.5. How are we getting a graph of f of x? Right? You could plot that a point at a time. Pick a value of x and then figure out what its y value is going to be. How do you find its y value? Well, you have to evaluate the function. To evaluate the function, you integrate from 0 to 1/2 t times t minus 1 times t minus 3 dt. Okay. How would you compute that? Well, you have the fundamental theorem of calculus, which says that you need to compute some capital F function evaluated at 1/2, okay, minus, let me be careful here with notation. Let me just say that it's going to be some capital function g minus some capital function 0, where g of x is an antiderivative of t times t minus 1 times t minus 3. Okay. Can you find that antiderivative? What is g of t? Okay. And you say, sure you can, because the function little f of t was t times t minus 1 times t minus 3. We can do some algebra. I think we've already done that algebra, t minus 4t plus 3. So you get t cubed minus 4t squared plus 3t. And so you can find an antiderivative of that function, which would give you g of t. So that would be 1/4 t to the 4th minus 4t cubed over 3 plus 3t squared over 2. Okay. There's your antiderivative. So now you can find the function evaluated at 0.5 by simply taking the antiderivative evaluated at 1/2 minus the antiderivative at 0. The antiderivative g evaluated at 0 will be 0 because each of these, this formula has a t in it. Oh, I'm sorry you can't see this. Let me let everybody catch up. I just expanded out the algebra on the function f of t. I'm trying to find an antiderivative so I can plug in 0 and 1/2 into that antiderivative. And when you plug in 1/2 into this antiderivative, you will get something around, let's see what the computer will say it is. It's not a hard thing to substitute in on your, okay, let me put 0.5 here. Okay, you will get for your answer something around 0.223. Okay. So that's how you are getting values for this antiderivative. You'll get 0.223, and you can graph this function a dot at a time, right? And that will give you the graph of the solid line. Okay? So in this video, in the next video, we will we'll try to address function capital F of x where you can actually find the antiderivative.